Thursday, week 14, 1 p.m. to 4 p.m. So plan for like a 2-hour test. So the time is 1 p.m. to 4 p.m. And some of you may start at 1, others at 1:30, and others at 2. That's kind of what I'm thinking. Or all of you may start at 1. But I'm thinking of like a 2-hour test. So mark the date, December 9, Thursday. All right. We were talking about functions last class. So I think we kind of talked about how lambdas work. I'm not sure where I stopped, but I have a question for you guys. So what I'll do is I'll type up the question, okay? So everybody can see, even if they can't understand. Let's say you have a standard container and you have to use lambdas because my script, when you type in, will look for the lambda. You can't solve it any other way. For example, by trying to do write function objects, none of that stuff will work, right? So it has to be one single statement, and it will search for obviously all the syntax that a lambda requires. So here's the particular problem. You're given a sequential container. Let's suppose it's a vector, right? So given a vector, let's say of integer values, I'm going to ask you, how will you find the first value that is between the interval x and y, where x and y are some numbers, right? And so obviously you need to return a iterator, and we'll print that iterator or the element that the iterator is pointing to, and based on that we'll know whether your answer is correct or not. What would you do? And this has to be done in one single statement using lambdas.
So you can repeat the question because
Yeah. Oh, you can't see it?
No, I don't really understand the question.
Okay, you're given. Okay, I'll put it in game terms. Okay, you have a list of high scores, right? And you want to find the first person, let's say, or the first value of scores in the range from x to y. So you have just a vector that contains scores, right? Maybe based on the order in which the players played. So it's not sorted or anything. It's just a bunch of numbers. And you need to find the very first score in the range x and y, where x can be anything, y can be any other value.
Can't you just return the array x? How do I?
This is not an array. This is the range.
Range. Oh.
In a range, so you have a vector container that contains a large number of values, and it's not sorted. It's just numbers. You need to find the very first value in the range from x to y, where x and y are, let's say, given to you.
Standard find if.
Find if is, I think, yeah, good. So since I don't have access to, let's say, writing code, it would just basically look like this. Begin container, oops, begin container, end container, and X and Y, right? They're given as variables that are in the scope. So you need to capture them. So what is the syntax for capturing X and Y? How would you capture them inside your Lambda?
By value?
Sure, but what do I do next? What do I type?
Equal.
But there are lots of values. Is it okay to just do this? Are we going to capture every single value out there? Are we just going to capture only the 2 values that we need? Is your code going to be really slow if you do this? So you're going to type in, if the, hang on, I'll call this A, right, or I. So you need to check if X is, I is greater than or equivalent to X, and I is less than or equivalent to Y, right? And that is your Lambda. And the answer is correct simply because even if there are a million elements defined in the scope of the function in which this particular function is being called, the thing that you guys need to remember is that you're not capturing all of them. The compiler, when it instantiates the closure or the class that is associated with this particular Lambda, is going to look inside and say, oh, okay, we only need X and Y. So I don't need to capture all of the other variables that are defined outside, because they could be vectors, they could be lists, they could be all kinds of things. But you don't need to worry because this syntax will do the trick because you're only making use of 2 guys in that scope. And if you want to be more correct, then you specify the return value by doing something like this. Although the nice thing about function templates is that our lambdas is that it is deduced that the return is going to be a bool. Okay. Given a vector, so again, everything has to be done in one single statement. How will you write or overwrite the contents of the container with the cube, the value? Anybody?
Standard replace with the same trick again.
Replace. I don't know if I've heard of replace, to be honest. Is it a new function? Okay, there are no hits, my friend. Ah, there is. Never heard of replace. That's because it's kind of new. So you are way ahead of everybody else, whoever gave the answer. I mean, yeah, it looks like replaces all elements satisfying specific criteria with new value in the range from first to last. Okay, but this is pretty new, so I'm not sure if all of you are aware of this, because there are right now almost 100 functions, right? So the ones you need to remember are the ones we discuss in class. And the ones I discuss are the ones kind of that are more commonly used before all these new ones came along. So I was thinking of the transform. So that is the purpose of transform, right? It takes the container begin and container, and then you can give it again the same range, and then you specify a lambda with the return value essentially being like this. The trivial replace probably looks similar, but this one I think is easier. So these are the little things that you guys need to kind of review, right? I'll, all the things that we've been doing in class. So most of the quiz, the test, is going to be sort of simple questions, but similar to this. Oh, I have some trick questions up my sleeve. Here's one question. Suppose C++ doesn't allow binary functions. When I say binary functions, it means that you can't write functions that take 2 arguments, okay? So how can you then write a greater than function? Greater than means I have to compare 2 things, right? A and B, X and Y, I and J, whatever. How can you write a greater than function that makes use of lambdas? How can you write a greater than function that that is unary? That is a unary function and makes use of lambdas. Not a trick question. It's just that sometimes when you deal with functions, you don't need the ability to write functions that take more than one argument. You can actually do anything you want using just one single argument. And this is a little bit harder, so it's going to be worth 10 points. The previous questions were worth 2 points, just so that you know. Okay. All right. I'll actually cover this today. So pay attention, because I don't think you'll have time to make up. So every day, please spend a little bit of time. So I kind of remember essentially, let me quickly kind of does anybody recall where we left off? For some reason, it's more than a week and I'm kind of lost track. Let me begin here because this is a good point. Actually, this. So, because just so that everybody is aware of the syntax. So in this particular syntax, okay, we are, so the square brackets that you see there, this one and this one. So obviously we are dealing with lambdas. Sorry to jump in because. So this is called the capture list. And this particular syntax, we're not capturing anything. We are actually defining a sort of like a local variable. And that particular variable, the syntax for defining a new variable called numbers looks like this. So in the corresponding class, what happens is that numbers is going to become a private data member, right? And this particular object is not being changed. So that is why you don't see the mutable keyword. The mutable keyword, which is one of the optional keywords, comes in here. Need a pen, but Dell doesn't sell one. So here we put the mutable keyword. If you decide that you want to change the contents of this particular list called numbers. Because it is not mutable, this particular variable is going to be sort of unmutable. It cannot be changed. And this particular function that I circled here is going to be labeled as a const member function. So keep track of all the little nuances with lambdas. I'll give you a little quiz that you can take home and use it as a learning sort of thing, because this is obviously sort of a fairly common thing that you do when you use modern C++. Did we cover this, guys? So this particular picture to the right is illustrating what happens when you write a lambda that you see on the left. The compiler is transparently, right? All this is hidden from us. We don't know what the names of these classes are, but what it's doing is that it's creating a class that obviously overloads the function call operator. So the lambda is a callable object. It kind of behaves like a function, so is a function, and therefore within this particular class, they have to overload the function call operator. And this particular class is different because it contains state, right? The state that it acquires is the list of integer values. This is another example where you are again, right, defining a variable y, which is of type reference. So y is going to get a reference to x. And this is obviously useful when you deal with unique pointers because they're not copyable. So if you are interested in taking advantage of the unique pointer that is specified by x, then the only way is to move that particular unique pointer or to get it by reference. This is an example of the mutable keyword. So I'm defining a variable, internal variable called count. And notice that we are changing the value of this particular variable. So the count is going to become a internal data member. And there the function that implements the excuse me, the function call operator is no longer going to be a const function because you are changing the state of this particular data member that you captured. So the picture looks like this. Here, do you see what does this syntax mean? We are making a copy and we wish to change. So we are copying by value, but I wish to make changes to that particular value. And the only way to do that is to take a personal copy of that particular variable. Let me see. I don't know if we did this, but this is the syntax for capturing by reference. The most important thing that you need to worry about is if you capture by reference, right? And this lambda can be used anywhere else. You got to make sure that this doesn't go out of scope. The important thing for you to understand is that the lambda, when it gets instantiated, okay, here, what happens is that you're making a copy of the variable. If this variable changes somewhere here in between these two calls, that is not going to affect the value that got captured. It's internal. While with the reference, it's not internal. So any changes that are made to this particular guy will be referenced still by your variable because you have a reference to that variable. And if it goes out of scope, you're in trouble.
Professor, can I ask a question?
Yeah.
Then wouldn't make pass by reference non-cons already also? So it's like a mutable lambda.
So
Yeah.
you're saying when should it be just reference and when should it be read-only reference?
When should it be reference and when should it be mutable?
It depends, right? It's why you pass by value and why you pass by why you pass by reference, L value that is, and why you pass by L value reference to read only. So the idea here is that you want this particular lambda to update this guy. Others might be changing it too, but you want to certainly participate in that process. If you capture the reference only by a read-only reference, then obviously this can change by itself, but you can't change it.
Okay, I understand. Thank you.
Yeah, and here's the other interesting thing. Notice that this particular function is going to be declared as const. I hope everybody understands this particular point, right? This is const even though you are changing the value that this is referencing. Why? Because v itself is not changing. It is something else outside the class that is changing through v. And it's the same idea between pointers. If this was a pointer variable, let's say, as long as p is never pointing anywhere else, that's fine. Then, the object is considered const. But using p, if you're changing some other location in memory, then the 8 bytes that are associated with this particular object are never changing. So as far as the constness is concerned, you can still pass a pointer to a read-only, right? So I think we saw examples of this in the midterm too. This is an example where I think, I don't think I covered this as I recall. So this is simply showing you all the different ways in which you can reference, right? So it's encapsulating all of the previous slides. So notice that these guys are in scope, so you can certainly capture. And as I indicated earlier, when we were discussing, whether this syntax is okay. What if you have lots of variables? Are you capturing all of them? No. The compiler will only look at what are being referenced inside the lambda and capture them by value. So in other words, only those variables that are being referenced will be initialized using a constructor that we don't have access to by the compiler. Then when you say capture all variables by reference, again, the same idea comes into play. You're only going to capture those variables that you are referencing. Here, you're capturing the entire object by reference. This makes sense only when you have a member function, right? Which is exactly what I have here. Inside the member function, I have a lambda, and that particular lambda is capturing the entire state of that particular object to potentially do certain things with, the data member here, for example, associated with that particular object. And here I'm making a copy. So this is the pointer, and this is you're making a copy. So basically, I mean, I think although it's true that only the variables that you're actually using are the ones that are being copied or referenced, I generally don't think it's a good idea for you to just blindly go in and do this because maintenance is going to be hard. You have sort of I mean, it's harder to understand for people who come along later on to understand what exactly are the specific things that you need to actually reference. And those things change as people update your Lambda. So I don't know. I just kind of stay away from these sorts of capture all. Um, the so you can, in this particular case, I'm capturing everything. But here, what happens here is that even though I'm referencing all three, A, B, and C, because of what you see here, the compiler is only going to capture A and B by value, and C is going to be by reference. And the same goes, it's going to capture A and B by reference and only C by value. So you get sort of like slightly more complex syntax. Did I say that earlier? Yeah. So probably I'm trying to emphasize the fact that I don't think it's a good idea to capture all variables. The most interesting thing for you guys is that when you don't capture, the lambda is implicitly converted to a pointer to a function. OK, and this special symbol is required to allow the compiler to actually perform that particular conversion. So I have some sort of a UI related function. Obviously, when you press a button, anybody who's done any sort of graphics programming or UI programming knows that, when we press a button, we want some behavior to be implemented. And the idea is that we can plug in all kinds of different behaviors, for different kinds of buttons, right? And this is a pointer to a function. And here I have a lambda that does something. And notice the signature. It takes a int and a pointer to a read-only char, so some sort of a C string potentially. And this guy has exactly the same parameters. And the most important thing is there are no captures. And this guy is going to be considered by the compiler to be no different than this. And the compiler will allow you to pass the lambda without any work being done. Implicitly, the lambda is going to be converted to a pointer to a function. And that is quite important because any other conversion is actually quite expensive. And we'll look at the different ways in which we can combine function pointers, function objects. What else? We can combine lambdas, all of them into one sort of container. Um, so captureless, they seem to become function pointers, but lambdas with capture, each one of them is going to have exactly, a unique type, right? And even if you make them be quite similar to each other, what I've noticed is that they have their own unique type, but in the latest version, I can define a lambda with a capture and assign it to another lambda. So I think the compilers are constantly being updated with new and stuff, and it's going to be hard for any one of us to constantly keep updating because I actually don't like the 3-year model. It's just too much. I don't know how any human can keep track of all the things that are going on. It's just impossible. OK, so here's a particular problem. OK, I have this particular function that I wrote myself, and it's a function template. Just to give you an idea that we should be able to write these function templates. Obviously, this is going to allow me to implement this particular function for a variety of different unary functions. So f can be in literally any type of unary function. And what you will see is that just like with the standard algorithms, this can be used with any kind of callable. So I call it a callable, right? It could be a function pointer, a class that overloads the function call operator, or just the lambda expression that we wrote. Now, obviously, we can call it many different ways. So here are some examples. So for up to here is being called, for a bunch of it's being called, it's being instantiated. A version of this particular function is being instantiated for this specific type of f. So f is the template parameter. This will have its own unique type. All right. And if you capture, maybe rather than a vector and you instead capture a list, well, you're going to get another template, function template instantiated. If you change, rather than a pushback, you do something else like emplace back, well, you get another function instantiated. So what happens is that if your lambda is a little bit sizable, or this particular function is a little bit sizable, then the number of instantiations could reach thousands, right? So here I'm instantiating it with a pointer to a function that is instantiated only for template parameter int. So one of the problems using these sorts of algorithms is that the size of your code can increase, especially if this is non-trivial. In other words, if this is big enough and you're doing some complex stuff, well, the amount of instantiations, thousands of them, can first of all lead to potentially, some guy at Ubisoft was telling me sometimes it takes hours, and that's why they try to reduce the number of function templates they use and class templates. Even though much of the work can be done at compile time, it's just that they find that in a non-trivial environment, the amount of time that one has to wait for the entire thing to compile just becomes, larger and larger and larger, because the compiler has to instantiate, this particular function, then compile it. So there's quite a bunch of work being done. With non-templates, what you can do is you can compile those source files containing these definitions, non-template definitions, and all you need are the object files, right? And you can take those object files and put them in libraries, and you simply need to link. So compilation times are never going to be a problem in non-template environments. So as I sort of argue here, one way to kind of Ubisoft might solve the problem is to say, you know what, let's go back and take a look at this function template and reorganize it as a non-template function. All right, just a plain old function. And what they do is they simply specify a pointer to a function as one of the parameters. So remember, this is a function that enumerates values from 0 up until, but not including the value n, and then it calls the function f. So you are basically calling the function f of 0, f of 1, just like a mathematical thing, right? There is some sequence of values that are being enumerated and you're applying this function. And obviously this is going to work for pointers to functions. And as I indicated earlier, it will work for templates that have the plus symbol indicating that they are capture-less. But what about all the other lambdas? There are, lots of lambdas that you may wish to use with this particular non-template function. So how can we reconcile the idea of, static polymorphism, which is what function templates are, with the cost associated with them, especially in terms of compile time? So this is one solution, but this is not going to work because you can't use it with lambdas. You can only use it with anything that is not a lambda, but it's still callable. For example, you can get pointers to member functions, and you can get pointers to ordinary functions. So that is not going to be a problem, but it's going to be a problem for lambdas that capture state. So this not a problem because there's no captures, but this is going to be flagged as an error because you are capturing some state. And this entire thing is going to be treated by the compiler, this thing, not as a pointer to a function, but a slightly more complex class-based object. And so presumably you need some template magic to get to the underlying pointer to member function syntax, which apparently is not readily available. So we have a problem here. And the way that they fix the problem in modern C++ is that they invented this particular class, right? It's ready-made. It's built for you. It uses a lot of template magic. It actually is something we can actually discuss. It just takes 1 to 2 weeks, right, of discussion to kind of dig into it. And I'll speak a little bit more about it in a moment, but let's continue. So let me get rid of this. So the syntax looks like this. This is a polymorphic type, right? When I use the term polymorphic, what I'm really talking about is internally, this is a class that uses some wizardry that involves runtime polymorphism, which in turn involves virtual functions to negate the need for static polymorphism, which is what templates do. So I think of it as a bridge between static polymorphism and runtime polymorphism. It is actually internally implemented using runtime polymorphism, and it allows us to sort of be in between templates and in between inheritance based on virtual functions. And the way so it's a wrapper. It is a wrapper that allows you to wrap this guy. It allows you to wrap this lambda. It allows you to wrap this particular function or pointer to a function. It allows you to even wrap member functions of classes. So essentially anything that looks like a function that has this particular signature that you see here. Oh, I'm going backwards, excuse me. That has this particular signature. The signature here is a function that takes an int and returns a void. Anything that looks like a function, behaves like a function, that takes an int and returns a void can be wrapped, right, using this particular class type. So this particular class type is sort of like a superset that allows you to describe anything that can behave like a function. And it was solely implemented in the standard library, came in 2011. It didn't exist before that. So it came with lambdas. It came with another thing called bind. So, so let's kind of take a moment to look at it and see what are the advantages for you guys and what are the disadvantages. So what we are doing then is we started with a function template like this. We said the cost could be high. They're certainly going to be high in a non-trivial application. In your own games, probably not. But what happens is that we didn't want to bear the cost of sitting around for hours waiting for our stuff to compile. So we converted into non-template. But then that led to certain lambdas or anything that was capturing state couldn't be supplied as one of the arguments to this function, right? Because this is a distinct type, pointer to a function that takes an int and returns a void, and ordinary lambdas cannot be cast to be of that type. Only captureless lambdas could. So the designers of the language of the standard library, they invented this polymorphic wrapper, right? that takes you away from templates, but it takes you closer towards inheritance. So its internals are done using internals and using a particular mechanism called call type erasure, right? Because that's exactly what's going on. We are sort of nullifying using this wrapper the individual type. One is a pointer to a function, one is a lambda, one is a function object, all that disappears because we can throw them all into this particular type, right? And we can have objects of this particular type represent, be substitutes for each one of our individual functions, function objects, lambdas, and so on. So unfortunately, we don't have the time to discuss the internal details. It's quite interesting, but certainly it will take a week just discussing that. And it's quite an advanced topic. And you know, I'm not entirely sure how practically useful it might be. But if anybody's interested, next semester, I'm more than happy to talk about these things because I certainly will have more time. And if you do, then you can contact me. So guys, here's a working example. What I have is a container, right? Because that is how you're going to build your UI systems, all right? You have a lot of different things that people can press in terms of UI. And for each one of these, you decided, okay, in one scenario, I'm going to write a on plain old function. In other cases, I'm going to rely on things that come from the standard library. For example, this is a function that is implemented in the standard library. Or you can write your own lambdas, which I'm doing here, and so on and so forth. And all of them can be thrown into this particular container because this container is going to contain every element that is of this wrapper type, right? So let's kind of look at the individual things. So multiplies, by the way, I should indicate to you guys that even though lambdas have been around for a while, lots of people still use function objects. So since I'm here, I should show you guys. So we should look at the, can somebody see functional? There. So when you go into this class, okay, we actually have quite a lot of popular containers. And I think you should be familiar with some of them at least because there's no particular reason to write a lambda for everything, right? There's a whole bunch of stuff and they're commonly used. And anything built in the library, I have a feeling is going to be better than even the best lambda you're going to write. So all of the basic stuff, if you want to add two things, you want to subtract one thing from the other thing, you want to multiply, divide, all of these things, all of these exist. These are the newer 21s, but they are logical, bitwise. They're called function objects, okay? And they're implemented using simple classes, predicate classes, some of them. Others are just binary functions, plus, minus, etc. And generally, when you come to the midterm or the final, if you know some of these, your life is going to be a whole lot simpler because you have to just type less, right? And I'll show you many examples today of how one can use it. So multiplies, the one you saw me, looks like this. It is a function object. So you can see it's a class-based object, actually structure, because it doesn't store any state. So part of one thing we need to learn is that If you're not storing any state, declare that particular class as struct, otherwise declare it as class. And what it does is that it's a function object that implements the multiplication, and generally speaking, all of the type deduction is going to be done completely by the compiler. So you can kind of not even worry about specifying, for example, since 2014, or is it 2017? I'm not entirely sure. For example, if you are interested in multiplying two ints, you would say multiplies, and then you would specify the int, type. But with classes, I believe it's 2017. You no longer need to do that. For example, even the vector class, you simply can write code now that says std vector, right? You don't need the, don't need to explicitly specify the template type parameter. The compiler will deduce that from the initializers, for example. So std vector vi with 1, 2, 3 as the initializers in an initializer list, the compiler will deduce. So what it could do for functions, it now does for classes. I'm quite sure it's from 2017, not 2014. So anyways, there's a whole bunch of stuff. And so there's very little reason for us to unnecessarily write code. So when you see these things, I'm specifying them from the library, right? So the idea here is that I'm explicitly asking for float. So can somebody explain what it means to explicitly ask for float? I mean, when you let's say write a function template and you explicitly specify the template argument, right? Like float. What does that mean? It basically means that even if you, for example, take your vector class and say, I want int values, but you are providing initializers that are not necessarily ints, right? Obviously not using the initializer list, but other kinds of initializers if possible, then the compiler will convert those initializers from whatever type to the int type. So if you have a function template that compares two numbers, then both numbers have to be the same type. But if you pass one argument to be of type int and the other to be of type float, as you are well aware, the compiler is going to be unable to deduce the single template parameter. T can be either int or float, so the compiler gets confused and it says, I can't compile or I can't instantiate a specific version. But if you specify, for example, for a function template, this template argument explicitly, then you can specify whether the left or the right arguments to be whatever type you want, but the compiler will assume or implicitly convert, if possible, whatever arguments you specify to the float type. All right, so whether you specify ints, floats, doubles, whatever, they're all going to be converted to float. On the other hand, you let the compiler deduce the types, the template parameter type, then you end up with a problem if you specify the left and the right to be different. This one, what you're basically saying is, I want you to figure it out. All right, I'm not going to give you. So take a moment to look at the parameters that are being specified and using those deduce whatever is the type that you need to, right? When we make a call to this particular function object. So I'm adding two function objects, each of a different type. One is for floats and the other is a generic type. This one, I believe, is a function from the C math standard library, which does some variation of the max function for floats or floating point values. And here I have a lambda. As you can see, I'm intentionally creating a capture lambda. In other words, it's capturing the state. And there won't be any implicit conversion of this guy to a function pointer. But we are still able to add this to our container. So the container now is completely polymorphic, right? It has all kinds of different functions. The only thing they share is that all of them take two floats and return a float. That's about it. And this one is an example of what is called a generic lambda. A generic lambda, we'll look at it later, is essentially not a class template, but instead it is a class that contains a function template. So for one class, we can have many instantiations of this particular function that implements what you see here. Then you can see me iterate through each element of the container and essentially call these functions. So this seems like a pretty good thing that you want if you're building UI systems. Lots of different kinds of buttons, lots of different clicks, or you're building some sort of grammar systems like a parser for a particular programming language, a scripting language, and so on and so forth. Because there are certain things that are easily done using different kinds of callable objects, and there is a way for you to combine all of them. And actually, it's quite interesting. We can actually add member functions too. So this is a pretty nice example. So all of you know that in the string class we have the length member function, right? But there is no way for you to call that function, without actually thinking of it as a member function, without passing that particular function, this pointer. In other words, there's got to be a string. But notice what this function type does. We are declaring this particular type to be having the signature, right? It is the signature is, it is going to have a reference to the string type. It is going to return length, and there's nothing more, so it means it takes nothing, right? We don't need to add void. It takes nothing, and therefore it returns an integral value. So we have the return type, but we need to specify the class type, right? So that is the only additional thing that you see to the signature. And what I do is I get access to that particular function. It's a public member function, so I can get F, the wrapper, to actually get to reference this particular member function, the public member function. And when I later on have a string such as this, I can actually call that particular length member function of string without using the member function syntax. Instead, I let this polymorphic type figure all that stuff out behind the scenes. So if you have something in the library that is already implemented, there is possibilities in terms of, taking certain things that you see that are interesting in the string class and putting them in, creating your own list of these interesting functions. Of course, they have to have the same signature. So that is an interesting tidbit. I didn't know this, so I was kind of researching, and I kind of noticed that this is possible. I don't think it was possible earlier, but seems like it is possible now. And I can also take functions that we write, right? So here's a member function called func for some class C. And notice that it is a function that is declared to be const. And all it does is it doesn't change any state. It returns the product, right? I just call it func for no good reason, but it's really the multiply. So what I can do then is I can create a wrapper for this member function that looks like this. These two indicate obviously the two parameters are arguments for this particular function, but this is essentially what is the type, what is the class type. In our case, I want this to be a this is a read-only is a const member function, so obviously the reference has to be to a read-only object of type C. And once I create an object of this polymorphic wrapper type, which is unpronounceable, then I can make that particular function be a reference essentially to the member function C. And obviously, if I want to invoke that member function, I do need objects of type C. I can't just blindly call it because it's not a static member function. So here I'm instantiating a throwaway R value, a no name object of type C, and the compiler will take these two parameters and return 200. Right? So there is two more things we can add to the list of things for which this guy can behave as a wrapper. So essentially anything in C++ that is callable can become a wrapper and can be wrapped and stored in containers. So let me just show you a few examples, guys, because it could be useful if somehow. I think I was working here. So let's say you are implementing a simple dispatch table, vector table, or you're building state machines. Then here's a very simple way for you to implement such a template or such a state machine, dispatch table, vector table, whatever you want to call it. So let me show you how that works. We'll call it, maybe I have it. No. Okay. Okay, I don't have it, but let's go build one. But for some reason, I thought I had it. So this is sort of could be useful in your UI systems. There are lots of buttons, lots of different kinds of callbacks, some written, C-style functions. For some, you have function objects. For others, you wish to write lambdas. And so how do we create, a list of buttons? And the way you can think of it is, let's say I want to put all my buttons in a vector class, just like we did earlier. And I'm just quickly going to build a very simple class like this. And so each button is going to encapsulate its behavior, right? Inside this polymorphic type. And let's say they return nothing and they take maybe nothing for now. And this is your, let's say, handler. So whenever you press a button, you want something to happen. Well, this is the guy who's supposed to do that job, right? So we need to obviously build a simple constructor, and that constructor might look like this. So void. Let's see. So let's say you click a button, you pass that particular thing, and I'll simply go ahead and initialize my handler. So you're giving me some function, okay? And that function can be anything because it is wrapped in this polymorphic type, whether it's a member function, what have you. I'm still going to get access to it, and I am essentially making a copy of it. Then we need some sort of a behavior that I already used the click. So let's say we'll just call it click. And what this guy does is every time you click, some action needs to take place. And that action is implemented in this handler function to which you have a reference, right? And that's going to be of this type. So I simply go ahead and call. Notice that it takes nothing and returns nothing. So that's okay for us to do. Then I don't think we need anything more. This is good enough. So now I come into main. Well, let's say somewhere else somebody has actually created a list of buttons, right? So create buttons, and it looks like this. So we'll just make up a few buttons. Let's say Punk maybe is the name of one button. And what it does is that it essentially is going to take as the constructor. See, I'm creating a button, so I need to provide some behavior, right? And that behavior will be essentially supplied to click, because click is the parameter, and that in turn will be used to initialize handler. So let's write a lambda, right? And let's say we want to keep track of how many times honk, the button honk got pressed. So counter 0. So this is a good example of how I define a variable within the scope of this particular lambda. So it's going to become a private data member. And I am going to, let's say, make some sound, honk, honk, maybe. And yeah, and then print the counter. Because it's starting at 0, I'm going to print the counter. Does this make sense to you guys so far? Is there anything that is confusing here? I'm just making stuff up, but this is, hang on. Yeah, this is the function. Within the function, I'm defining an object of some lambda type, and I am asking the compiler to instantiate this particular parameter, which is declared to be of this type and can certainly wrap any lambda that you supply to be of that particular type. Any questions here, guys? Okay, so then what I'll do is I don't know. I'll call it the bark button, right? And the bark button, let's say, doesn't do any capture business. And what it does is that, it prints this beware of dogs and goes away. So this is the next button that we create. Maybe let's just go ahead and create a third button, and that is, we'll call it mute. And for some reason, it is mute because it doesn't do anything, as you can see. All right, so I have 3 buttons, each one of them I define like this. If you want, let's say you can actually create a button using a regular function or a function object, but let's not waste time because we have 3 good buttons. So let's go ahead and define a vector that is now going to contain this list of buttons. Is it button or buttons? Button. Honk, bark, and mute. And there's one thing I've been asked a couple of questions about this, right? We learned about RVO, NRVO, and we also learned about move semantics. There was a particular question from a gentleman, and that was, should you do this? Because you're returning by value, isn't it better? Hang on, did I forget to put something? Yeah. So the question was, should you move this stuff out? And the answer is no, you should never ever do that, because move is actually more expensive than RVO. RVO means you don't have to do anything because the guy to whom you're returning is actually the one that is going to be constructed if RVO takes place. So move might actually be a little bit more expensive, so don't do that. Okay. So instead, you should just return as you normally would by value and let RVO do the magic of not even having to move anything. All right, I'm hoping I didn't make any silly mistakes. If you're watching, please let me know. Don't embarrass me here because with all these templates and lambdas, I mean, we can chase these errors for a long time. So let's go ahead and create our buttons. The buttons are going to be so there we have, and then let's iterate through them. For each button.
Professor Prasanna.
Yeah.
Can the function have like return type?
Can have what?
Can the SCD function have a return type?
Yeah, so what I'm saying is give me an object that is going to be of type vector, where each element is of this type, and initialize 3 elements and then return that. So this is certainly there's nothing wrong with this, right? Are you saying that there might be something wrong with this? I'm constructing in place and returning. I don't need a name, right?
No, I mean, can one of the examples like the lambdas have a return type?
Lambdas, I see. Well, the point is that it depends on this, right? So I've chosen all of my buttons to have this very simple thing, so I don't need to do a lot. We can choose whatever type we want here. Because what am I doing here? I'm creating a button, right? And I'm supplying the parameter, the argument to the this highlighted thing is the argument to the buttons constructor. Okay. And our constructor is going to be of this particular type, the parameter, void. That is the signature, right? So if you say
So
return, it's
void can't have a return.
that is the signature of all of our callable objects. If you say return counter here, then we have a problem because it's going to have int type that is going to be deduced, but the compiler will not allow you to take this particular thing that you're constructing and allow you to wrap this lambda to be of this particular type.
Well, then how come I'm wondering the parameter can be void, but then the lambda can take in a parameter like counter equals 0?
Oh, it's not taking in a parameter. No, I'm actually skipping the parameter.
Oh, okay.
This is the capture list, right? And this syntax means define a local variable counter.
Oh, okay.
Right? Except when we use the term local, it kind of gives us the impression that as soon as this object is constructed, counter goes away. Counter is going to become a private data member within the closure associated with this particular lambda. So next time you call honk, each time you call the honk, then the counter will be incremented. And we are going to print that particular value.
Also, counter is like kind of like a static.
No, I won't call it static. It is a data member of the closure associated with this lambda.
Oh, okay.
So let me, these are good questions. I'm sure others have them too, but I think we actually were just looking at it. So it's nothing wrong in looking at it again, because that is the reason why I had some examples earlier. I remember, yeah, this one. So let me get to this. So what I'm doing here is numbers is obviously a object that is not being captured, but that is actually being defined. And we are saying that we want this guy to be numbers to be initialized to be nothing but this. That is the syntax. If you want it to be int, then all of this would just be int, or you would provide an initializer. So here, this is the initializer for initializing numbers, which is a list of ints with 2 elements, 4 and 2. So the corresponding closure will look like this. The numbers object that got instantiated is going to become a private data member. And there is a constructor that you see here that is not accessible to us. Maybe I should have put a comment, not accessible to us, right? This is the one that we can access. And since we said we did not use the keyword mutable, we really are forced to make this particular function be read-only. Because if you want to change numbers, then you got to provide that mutable keyword. And then the compiler will then declare the corresponding functions to be of the appropriate non-const type. So this guy numbers is going to become a private data member. So that is essentially what's going to happen in our case too.
Okay, thank you.
Okay, so we have buttons, so let's iterate through each button. B. And what do we do with each button, guys? We ask for the click button, right? To be the click function to be implemented, because that is the reason why this thing is coming in handy. And let me just compile, because templates are a pain. Once you have a big error, it's going to take a long time. Error conversion from void to non-scalar type. What's wrong with this? I don't see anything wrong. Maybe there's something wrong up ahead, thousands of lines up ahead. I'm sorry, guys. Just give me a moment. No matching function for call. So this is not doing anything. So what's wrong with that? It is mute, for God's sake. This is a mute button. So why is this not compiling? Well, no matching function for call. No matching function. Oh, none of them are matching. So did I do something wrong? Something wrong. Oh, maybe I didn't include the proper headers. Functional IO stream. So this guy is a class that is declared in this header file. I don't think I'm using anything else. Let's see. Error increment of read-only variable counter. Why is it read-only? Silly mistake, right? So we didn't say we want to change. And if you don't, am I putting the mutable in the wrong place? No. Let me.
It's after the.
So I'm putting it in the wrong
bracket.
place. You mean I should put it here?
Yeah, I think so.
Okay, we actually have it here, guys. Do you see mutable here? I saw it just now. That is the annoying thing about this syntax. You got it. That's why I want you guys to just review everything, right? Okay, you are right. All right. Well, if it doesn't work, just switch to the other side. Okay. It's quite annoying because I think it should be allowed everywhere. So anyways, here we are. Everything works. And I click. So let's see what happens. So mute guy doesn't say anything. Apparently there's a thing that goes on and we can actually buttons. I think honk is at the very front and I run the click action. And so this is sort of like a selective, obviously a little bit exaggerated, but you can see now, you know, honk being incremented to 2, but this is sort of like, you know, in my opinion, probably a particular use case. Because when you get this convenience of being able to wrap anything that can be called, okay, then it comes at a certain cost. And the cost is that this guy is actually implemented, as I said, it's a bridge between static polymorphism being represented by templates and runtime polymorphism represented by virtual functions. So this guy internally is built using virtual functions. It uses a certain technique, or particular idiom or pattern in C++ called the type erasure pattern. Obviously, each one of these individual guys pointed to a function that takes nothing and returns a nothing is completely different from a closure or a lambda, but somehow we are erasing the individualness of each one of these functions, or callables, I should say, and putting them into this container, right? And so it's quite interesting, but it is quite sort of detailed, right? And I don't know, a 12-week semester is enough to spend on this because it's not something that you will make much use of. How do we build this? That is what I'm talking about. This, I think, could be useful as I show you here. There's another example I can give you, which is, let's say, actually, I can come in here. All of you have, at least in the computer graphics class, have used maps. Maps are associative arrays. They associate a key with a value. They actually are binary trees. And what they do is every time you insert an element, unlike a linked list or a vector or a deck, the inserted element will be given the appropriate position within the container. And this is done using what is called a red-black tree, which you will study in the data structures class, right? So I'm not going to spend any time talking about it because they will do a better job. And it's always going to be sorted, which means it's like a dictionary, right? Every word in our dictionary is sorted. And you add a new word in our dictionary. The Oxford guys constantly seem to add stuff, and they will find the appropriate place. And when you go buy the new dictionary, well, it's not like the new words are at the end. They have been given the appropriate place. And that takes quite a bit of effort, because if I am introducing a new word somewhere, then all of the other words have to be shifted down. So typesetting has to be adjusted and so on and so forth. So it is going to come at a cost. But the beauty of the system is that once you purchase the dictionary, after all the hard work, finding words is trivial, right? It's so good that there is no better way of doing searches. For example, if you have 1,000,000 words, how many comparisons are required before you can find your word in the dictionary? If you are a human looking at a dictionary, no more than 20 comparisons, right? Because it's a tree. So you open the book at the halfway point. Well, your word is either going to be in the left side or the right side. What have you done? You got rid of 50%, 500,000 words from ever being looked at. Well, you're going to repeat that process. You again flip to the middle. Is the word you're looking for to the left or the right? Well, you got rid of 250,000. So already 750 million gone in 2 steps. And 2 raised to the power of 20 is 1,000,000 approximately. So 20 is the number of maximum iterations, the worst case, right? And 20 is obtained by applying the logarithm function. And there's nothing better than the logarithm. So that is why associative arrays or maps are quite useful. And this is a map that is going to have, in a dictionary, the word is the key, and the meaning, the description of the word, the meaning, the paragraph is the value. So we use a char if I want to build some sort of a state machine, a dispatch table, calculator, many use cases, right? And it looks like this. And I need a function. So I'm going to again maybe actually let's do double so that we don't do a void again. And it looks like this. This is going to be the key. This is going to be the value. Can you see how we can build a state machine or a dispatch or a vector table? All I need is to insert each one of the keys along with the corresponding action. And when you press a particular button on your calculator, the plus button, the appropriate function is going to be executed. So let's go ahead and build this guy like this. Make pair, just like it's a utility, right? Just remember we made a make unique, make shared pointer. This guy is just creating a pair of your char and this particular class type called function. And how do we do that? Well, plus is going to look like this. and I'm going to build my lambda like this. I'll don't want to stretch too far to the right, so I'll go double and then return A plus B. That's it. And let me see if I've taken care of the last parenthesis. So the insert, okay, allows you to insert, and you can also do it like this. This is the beautiful thing about an associative array. It gives you all this weird syntax because this is the key. When you look for a word in your dictionary, you're not going to access the dictionary using the meaning and then searching for a word. There are other, books that do that. You take the meaning and then find the word. No, here we have the word and we are looking for the meaning. So if the word doesn't exist, then we are going to add one. If this word already exists, then we're going to discard whatever action we are performing, right? So you can certainly do it like this too. But this is simpler for me, so I'm going to go ahead and do that. Let's just quickly copy and paste a little bit of stuff so that at least I have a few. Let's say minus, and then I go minus. So I go plus, and then I go divide. No, multiply, and then divide. Okay, so obviously they're all lambdas, but let me just take the time to compute another one. We'll call it the power function, right? The caret symbol. And what it does is that it is not going to be a lambda, but instead it is going to be simply a pointer to a function. We'll just call it the power function, right? Power function. And we can implement our power function like this. It has to have the proper signature. So this is a function that takes the base, returns and takes the exponent. Is that what we call it? Yeah. And we'll assume the exponent is integer because, or I can just call the power function, I suppose. Return std power be. I hope this is correct. Let me include this in just in case I need to. I probably do because I'm using the namespace std. So I think there is a function called power. I rarely ever use that function, but I think there is, mostly because students seem to use it. So that's how I know it exists. All right, so we have a map, we have a table, and now what we want to do is we want to invoke this particular table. How do we do that? Well, there is, let's go ahead and kind of do it like this. Std like this, right? And I am going to obviously ask for the addition operation, and this is how we access maps, right? The index operator, the subscript operator, has been overloaded to make it easy for us to search in the sorted list. I simply provide the key, and the entire expression will evaluate, that function I should say, will evaluate to the value. And what am I doing with that value? Well, I wish to call it. So I'm making it become a callable like this. Right, so you should see 8. Let me just quickly run through a few examples, and that becomes another sort of, I mean, it's a good example, I think, because all it needs is, I guess, somebody to kind of build something like this. So here we should get 81, right? So let's check for all of these operations. Okay. Well, I'm doing the multiplication here. I think this should compile. I hope. Oh, I'm doing this all in button. Okay. Map is not a member, so I forgot to include math. Don't know if I'm forgetting anything else. Oh, we didn't define the power function. Oh, we did define it. Oh, I have a missing thing here. All right, so now when I call it, I forgot to put the new line, but you can see now 3 plus 4 is 8. That doesn't make sense. Well, um, 3 plus 4 is 7. I have no idea why. Oh, 3. Okay, I'm providing incorrect arguments. I'm providing, yeah, it should be 3 plus 5, blah, 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 right? Anyways, so this is another example, guys. Obviously, in this particular example, you didn't see me do with function objects. We can do that too, but I'll leave it to you guys to sort of experiment. So there's lots of interesting things we can do. Okay. So this is sort of some use cases, some examples of using this polymorphic type that is built as a bridge between static and dynamic polymorphism, uses elements of runtime polymorphism. And this particular code also works. I tried it, so you should take a look at it because it's quite interesting. You are making a call to the string length function, but you're using a wrapper. And that wrapper is pointing to, is got a reference to the length member function, but you're supplying sort of this pointer, right? And F is making a connection between your this pointer and passing this pointer to this member function called length. So you can do this too. This actually works. So you can not just provide all the usual callables we saw, but member functions from the library and from your own classes. So it can do everything, right? If you take F, for example, and if F is not initialized in that very first line, and you try to invoke, then it's going to throw a, I believe it's a bad lock exception. So it can be like any other function pointer. That is the most important thing you need to understand. So what the library has done is that it's allowed the creation of a wrapper using some template meta programming techniques, deep techniques, to implement a wrapper that behaves pretty much similar to a function pointer. And the big thing about C++ is the introduction of more and more wrappers similar to this. There are so many that, you know, we only kind of have to have a general idea of all the new things that are coming out and be able to use them when you, for example, have a need for something that you kind of at the back of your mind know is something that exists in the language. I would say there's the convenience aspect, and then there is the cost. The cost that is going to be borne is the fact that these guys are implemented using virtual functions. So that is always going to be expensive, right? Than using, obviously, templated functions. Then if you have a non-trivial function that is wrapped by function class, then, for example, if you have quite a bunch of these variables and each one of them is sort of expensive, then it needs to allocate memory on the heap, right? And so that is obviously going to cost you. And lambdas are sort of like first class citizens, first class objects in modern C++, but these guys are some sort of a complex type that is a superset of all of the callable types. So lambdas can be inline for better performance, but not these guys. So these guys give you the convenience of creating a super wrapper type that can essentially, be a container of any type of callable. So that, in my opinion, is the big advantage. Now in the language, what they've done, this I believe is in 2014. In 2014, or is it 2017? I can't keep track, right? Everything is happening at the speed of light. What lambdas can do is we can have generic lambdas. What does it mean? It means, well, you can pretty much call this particular lambda with any pair of types you wish. The only thing that you cannot deduce are the captured items. In this particular example, v is being initialized to the value 3. So although we are using the catch-all auto keyword to deduce v's type, we all know that v can have only the integer type. So v is not generic. V will always be int, but v0 and v1 can be any types. And the only thing that these types must provide is the multiplication and the addition operators. So make sure you understand that. You cannot just go willy-nilly calling this particular lambda for any type. Those types must provide the multiplication and the addition, all right, functionalities. And these guys are actually going to be implemented as member functions. How should I say this? Member template functions. Remember, the closure itself is not templated, so it's not a class template. But inside that class that represents, the closure associated with this lambda, then we have a member function that is templated, and it is templated on 2 parameters, T0, T1. If you have more autos, then you have to parameterize that particular function over more template type parameters. And if you essentially call this lambda with the arguments 10 and 11, then this particular closure will instantiate an internal member function template for ints. All right, so it will create a concrete function just for ints. If you call lambda with 2 doubles, well, it will call it will instantiate another member function. So the closure is slowly growing. What happens if you instantiate the lambda with an int and a double? Well, you're going to instantiate a third member function. So that is, again, a well-known problem with templates. The cost increases. And so it gets implemented like this. As you can see, the captured element v is still going to be a variable of type int, and T0, T1 are the template parameter types for this member function. So this is something that you may not have seen before. A member, how do I say this? A member function that is a function template. I don't know if people use the terminology, but this is a function template, but is also a class member function. Okay, so more about how we can use these guys and how the compiler will instantiate. Nothing complicated here because we've seen earlier pictures. Then the only other thing I might add is that in C++ 20, instead of just the keyword auto, they allow you to actually specify the complete type. What does that look like? It kind of looks like this, right? Let's give it a shot. So I'm writing a generic template. Do I have vector here? Yeah, I do. So the names, there's no proper way to decipher. So auto is pretty much the only logical thing that we can call this, right? Unless you want to assign them to a function class. So lambda, so this is brand new syntax in the compiler. What it allows you to do is rather than just using the keyword auto, it allows you to specify something like this. Let's say you have a member function. No, not a member function. You are performing certain operations inside this particular. So let's assume it's a vector, right? Let's say you're getting a reference to it. And let's say for whatever reason, you had stuff like this. What can we do with vectors, guys? Length, right? So let's say you just wrote code like this. And I don't know, I think this might, yeah, maybe maybe we can return some sort of a bool from the lambda, okay? And the way we can do that is by returning v.empty, right? Okay. So the problem with what you saw here with the 17 model is that if you assume that, let's say there's only one parameter, and if you assume that, well, generally it should be a container type that implements this particular policy, right? Of, having a member function length and a member function empty. Then there could be lots of compile time errors because the lambda is being supplied parameters that are not container type. So in 20, they fixed that particular problem by allowing you to explicitly specify, hey, I want, right, my, instead of just auto, you are taking some generic type, and the important thing is that you expect the objects to be of this particular type, where you're assuming a vector container. Earlier, if you provided this and you didn't supply a vector, then you would end up with lots of error messages. So it's kind of, in a sense, a slightly cosmetic change. Okay, let me just continue on. What is the time, guys? I don't want to keep you guys too. Okay, we have some time. Okay, so we studied functions, but something that is quite important is what is called in the functional programming community partial function application. And it does exactly what you see here. So basically I have a callable. Imagine it is a binary, okay? And binary functions require two arguments or two parameters. But what if I make that binary become a unary by fixing one of the arguments, right? And what if the other argument is obtained from another binary function whose input, one of its inputs is pre-specified or fixed to a certain value. So what we have is then a mechanism to perform things that look a lot like mathematical functions. I want to compute y when you plug in x, you want to be able to compute ax squared plus bx plus c. That is the corresponding y. So your domain is going to be the x values, but the range is going to be the corresponding y values, which are ax squared plus bx plus c. And it's a lot easier to compose these if you are able to bind some of these arguments to certain pre-specified values. And this can be done using lambdas, but the only difference between doing it using bind and using lambda is that bind allows better state. Right? With lambdas, you got to write everything in place, and you got to set up what is before you so that you can capture the appropriate values. So lambdas are nice as long as there are not too many of them where you are basically left with capturing the same stuff over and over again in many different places. Maintenance becomes a problem because something changes in the function. Instead of ax squared plus bx plus c, maybe you want to convert it into a cubic function. There are lots of maintenance issues, right? So C++ gives you what is called bind to implement exactly this idea of partial function application. So we need some examples, and I have some that I've already written. Oh, I should show you. I did write this guy. Remember our timer from the memory pool, so I repurposed it. And what I did, guys, is I ran an experiment. OK, I use lambda and I use a function. So you see this? Let's go to the lambda thing. I have a lambda. Obviously, we have a plain, straightforward lambda that returns an integer value, right? 3 times whatever is the input. And what I'm doing with this is that I am essentially, I'll come to this keyword in a moment, right? But if that keyword is confusing you, then there's another way to think of it. Using T is declaration type lambda. But I am defining lambda here, so I'm going to move this guy here, and then we can replace this entire thing with T. So what am I doing here? Well, basically, I have a lambda. I am saying get me the type of that lambda and use the type as an element of as the type of each element of this container. And how big is the container? Well, I say give me 10 million elements. And what am I going to do with each element? Well, I'm going to fill them up with lambda, right? So if this is confusing, all you have to do is make sure you go to where am I? Go to the constructors, and where are the constructors here? And you'll see that the particular constructor I'm using count and value, right? I'm using number 3. So I say, give me 10 million and have each one of them be exactly the same thing. That is fine. Not a big problem for us. And then what do I do? I have this integer variable, and then I start the timer. I go through every single one of these 10 million elements. Each element is of type, I reference each element using type F, and then I invoke, obviously, because this is a callable, right? Lambda is a callable. So I call this function, or callable, with this particular argument. So V is going to be whatever this value is, and it's going to return that particular arguments scaled by 3, which I then use as the input to the next, right? So it kind of keeps the numbers going. And I switch off the timer when I am done with that loop. Well, with the function part, I have similar lambda, except I am wrapping it in this, really general type. And general means not well optimized, right? Because it needs to worry about all the different ways in which you can wrap callables. I have exactly the same kind of vector, except this is no longer just a lambda. Instead, it is going to be lambda wrapped as a function object. Then I repeat the process, and you can see the performance gain is quite great, at least on my machine, for lambdas. Uh, 1233 is almost 3 times more expensive because of the virtual class or non-virtual function mechanism and the lack of opportunities to optimize that particular code. So I was trying to talk to you guys about something before I got there. What was it, guys? Does anybody remember? Oh, I was looking for something and I said.
Bind.
Sorry, which one was it?
Bind.cpp.
Fine.
Bind.
Find. Bind. Oh, okay. Thank you. My mind was totally bind. Yes. All right. So let's go here. And basically what we're doing is function composition, right? The ability to take the small lambdas or any such callables and combine them using that partial function application technique to create things that are more complex. And this is what I'm doing. So transform, as you can see, is a good place. What does transform do? Well, basically it allows you to take the contents of the source and apply some unary algorithm. Because there's only one x, right, coming in. There's no x1 and x2. So there's only one x. You apply a function to that x and write the result of whatever f the function returns, and you are inserting it. Notice that the deck is empty. So I got to use this iterator adapter, right? I've shown you front inserter, back inserter. They're very nice because we don't have to sort of, initialize these containers ahead of time. Okay, so what is going on? What is this partial function application? Well, I have this lengthy thing with lots of weird stuff. Bind is a function again that was invented in 2011. There were older versions that are completely deprecated. Okay, so bind and function are the ones that are new, and they came along with lambdas. So whether one chooses to use bind, whatever you can do with bind, you can do with lambdas. Whatever you can do with lambdas generally can be also done with binders. The question is which one is the most convenient, right? And most people are of the feeling that lambdas are the most convenient, but when you have many of them, maintaining them is a problem because, as I explained, changing things might mean you have to change in many different places. And if you're defining an object, then you're losing the whole point of defining in place. The whole point is that I didn't want to write a function object. Instead, I just wanted to write the actual code that I want and move on. So anyways, lots of promises from that perspective, but here we go. So I have the container source, I apply a function and I write the result back here. But this is a binary function. Multiplies is a binary function. It needs two inputs, x1 and x2. I have only x1. So what I'm saying here is that this is going to be a placeholder for whatever input that can be supplied to this so-called unary function now, because the other input to this binary function has been tied as set to this specific value 10. This is a good example of partial function application. I am deciding that one of the inputs always is going to be 10 unless somebody comes along and changes it. But the other one is going to come from the source. So as you read each element, that particular element is going to be scaled. It's going to be the assigned to this placeholder, and then the multiplication object is going to multiply what you just read and this pre-specified value. So what is really happening here is you're taking each element of the array and multiplying it by 10. So what you write back into the deck are going to be numbers that are scaled by a factor of 10. And this is a special syntax. It's easy for us, no, well, I wouldn't say easy, a little bit of work for us to write it for either the left or the right. In this particular case, you can choose. They can do lots of interesting things, these guys. So let's say if I'm able to compile everything. Oh. What's going on? Yeah. Oh, time's ticking, guys. I'll very quickly convert all of this next class. Then I'm going to move on to two new things that have shown up in C++. Very briefly, I quickly want to cover template argument deduction so that all of you can understand the auto and the declaration type. Then we'll also understand what are called forward references, because we need to kind of get to know these things. Then I also think we want to complete variadic templates. Now, I hope to complete all of them, but I also don't want to just rush through, right? Just give enough examples and give enough so that people will be able to kind of understand rather than thinking of it as just a skim through. So that is my hope for next class. This class, I have a few like 10 or so quizzes and I'll load them up. When is the assignment due? Guys?
I think it's Friday 8 AM.
Friday. Okay, maybe I'll have another one ready. Okay.
Friday
This one-
morning.
Okay. I mean, it wasn't a difficult one. I'm assuming most of you are done. I mean, that's what holidays come for, right? I'm just kidding. But I'm going to give you guys one on functional decomposition, because composition, I should say, because you will see how we can compose functions, sort of use the pipe feature in Unix that you are sort of familiar with, right? Because you learned it at least in the early part. Whether you use it or not, I don't know. But using that sort of an idea, I want you to be able to kind of write code that kind of allows you to compose more complex functions using smaller functions. And I'll probably also have something related to lambdas are not using lambdas, just to make it be a little bit more interesting. So I will be able to kind of definitely give those before you come along to Friday. Okay. And that should basically kind of, I might have some tutorials for you guys on templates so that you guys can review your knowledge, because there's quite a lot. We covered quite a bit in HLP2 templates. We covered template overloading, specialization, argument deduction, class templates, instantiation, member templates, quite a bunch of stuff, default arguments, non-type arguments, and so on and so forth. So maybe a simple, rather than going through that material again in class, which has got to be just a rough overview, I'm going to try to see if I can add some stuff for your final exam, sort of like review plus think of it as lab. All right, I'll see you guys on Thursday.
Hi, Professor.
Yep.
I have something to tell you.
And
No? Can you hear me?
sorry, I can't hear you. Is it private or do you want to say it in front of everybody or?
It's regarding about like one of the quizzes.
It's regarding one of your
Hello?
quizzes?
Yeah.
Okay, I mean, I think it should be done in private.
Okay.
I mean, are you in my other class?
No.
Okay, well, why don't you quickly call me on the other channel on my own thing, and then I'll get out of this one, okay?
Okay, thank you.
Yeah, no problem. All right, guys, see ya.
Sorry, Prof, what time is your consultation later?
I finished the other one, so probably 6 to 7. That is the normal time.
Okay, sure.
So normally I'm there, okay?
Mhm.
Even if I use phrases like probably, I'm generally there.
Okay.
Okay.
Sure.
So you can actually look at the record. It always says there's a meeting on.
Okay.
All right.
Thank you.
No
Bye-bye.
problem.